This video is about a technique called UV visible spectroscopy. So what does spectroscopy mean? So the general idea about spectroscopy is that molecules can absorb radiation or light. So here's our little molecule here in its ground state, and here is some light shining on the molecule, and the molecule can absorb that light, and in doing so the molecule gets promoted into this excited state up here. So there's a couple of important points to note here. The gap here between the excited state and the ground state, the energy gap here is characteristic of a particular molecule. This is related to the structure of the molecule in some way, this gap. The other important thing to note is that the wavelength of light, the energy of light shining on the molecule has to match the energy gap here in order for this transition to occur. So the general principle is you shine light onto a molecule and you observe which wavelengths are absorbed, and that gives you some information about the gap here, which in turn gives you information about the structure of the molecule in some way. So the nature of the transition and the nature of the excited state depends on what type of light is absorbed. So for example, here's our electromagnetic spectrum again. So for example, if you happen to shine UV light onto the molecule and the molecule absorbs UV light, then the excited state it gets promoted into will be related to electronic transitions. So electrons getting promoted up into higher energy orbitals. That type of transition corresponds to UV light. If a molecule absorbs infrared light, then it will be promoted into an excited state, and the excited state is a different vibration mode. So the difference in energy between vibration modes typically corresponds to infrared light. And finally, we're going to look at some low energy spectroscopy as well. That's when you shine radio waves onto a molecule, and if a molecule absorbs radio waves, it'll be promoted into an excited state, and where it's a different spin, it's a different type of nuclear spin, and the difference in energy between different types of nuclear spin turns out to be equal to the energy of radio waves. So the one we're going to look at now is UV light and electronic transitions. So what do I mean exactly by electronic transitions? It turns out that if your compound absorbs UV light, it's said to be UV active, and it's typically compounds that contain double bonds that absorb UV light. And the energy of the UV transition varies depending on the nature and the number of the double bonds. So the most UV active compounds are generally conjugated, which means they contain alternating single and double bonds. So here's some examples here of compounds that contain alternating single and double bonds. So you can see here goes double, single, double. Here we go double, single, double, single, double. And here's double, single, all the way around in a ring. So it turns out that molecules that contain this alternating pattern of double and single bonds, which are said to be conjugated, these types of molecules tend to be good at absorbing UV light. And remember, what's happening when the molecule absorbs UV light? An electron is getting promoted up into a higher energy orbital. And so that's the excited state that we're talking about here. So that means if a molecule absorbs UV-vis radiation, it probably has a conjugated system within its structure. So here's two examples you can see where the molecules contain a conjugated structure. And then the molecule down the bottom here, you can see it's got a very, very long conjugated structure. And so it turns out that the longer the conjugated system, the smaller the gap between the ground state and the excited state, so the lower energy light is required, which translates into a longer wavelength. So you can see here the absorption wavelength here is longer than for these shorter conjugated systems. So this compound, by the way, the bottom here, beta-carotene, that's the colour that gives carrots their characteristic colour. So double bonds can also contain heteroatoms like oxygen, nitrogen, sulfur. It doesn't just have to be all carbons. So here are two molecules that are also conjugated. So you can see here on the molecule on the left contains a double, single, double pattern there, and the pyridine here contains a double, single, double pattern around the ring. It doesn't matter that they happen to contain oxygen or nitrogen. So here's some other examples just to finish off with of some other molecules that are highly conjugated. So you can see the conjugated systems within these molecules. And so the larger extent of conjugation gives these characteristic wavelengths of absorption, and that's in the UV range. It turns out that these molecules are very useful as sunscreens. So these molecules are commonly found within sunscreens, and they absorb the UV light and stop it getting to your skin. So as far as you need to know for this course, how to interpret UV-vis data, this is pretty much a yes-no issue for you. So you just need to know, does the molecule have an absorption in the UV-vis region? If it does, you would say our molecule contains conjugation. If it doesn't, the molecule does not contain conjugation. Simple as that.